Hi everyone, in this video we want to go over the alternating series test. We can apply the alternating series test on alternating series. Alternating series are in the form of sigma -1 to power n bn or -1 to power n minus 1 bn, and n starts from some natural number and goes to positive infinity. So what is the alternating series test? Or for short, alternate AST. Alternating series test says that if an alternating series in the form of sigma -1 to power n bn satisfies this condition. The first condition is the series should be alternating series, so it should be contain -1 to power n or -1 to power n plus 1, -1 to power n minus 1, and the term of this series should be positive, negative, positive, negative, or negative, positive, negative, positive. So it should be in this form. And also for all n, bn should be positive. So bn, it's a sequence contain positive numbers, and then bn should be a decreasing sequence. So bn, it's monotone decreasing. And all terms are positive, then if the limit of bn when n approaches infinity is 0, then you can conclude that the series converges. Then sigma -1 to power n bn converge. So by alternating series test, we have an alternating series in the form of sigma -1 to power n bn. And now when we have -1 to power n and the sequence bn contains all positive terms and it is a decreasing, if the limit of bn when n approaches infinity is 0, then this alternating series converged by alternating series test. The alternating series test also help us to find the remainder and estimate the remainder. Previously, we learned how to estimate the remainder by the integral test. So by using the alternating series test, again, we can estimate remainder for series. So how we can estimate the remainder? Again, all the condition for the alternating series test should be valid here. So we have alternating series. Bn is a sequence of positive numbers. It is decreasing, and the limit of bn when n approaches infinity is 0. Then we can estimate the remainder by the alternating series test, and absolute value of Rn is less than the n plus 1 term of the sequence B. So Bn plus 1 is greater than absolute value of Rn. And in this case, we can estimate the remainder. Now let's solve some problem together. Here we have a series of -1 to power n over a square of 3n plus 2. This is an alternating series. Let me rewrite it, and you see this is an alternating series. It is -1 to power n times 1 over the square of 3n plus 2, and n starts from 0, goes to positive infinity. The first condition that we have for applying the alternating series test is to have -1 to power n, and because n starts from 0 goes to positive infinity, so the first term is -1 to power 0, which is positive 1. So the first term is positive. Then the next term is n1, and -1 to power 1 is -1. So the first term is positive, the other one is negative. Then the third term is positive, the fourth term is negative. So there is alternating sign here. And then we have sequence Bn here. As you see, numerator is positive, denominator also is positive. So for all n, I know that Bn, which is 1 over the square of 3n plus 2, is positive. Also, you can find the derivative and prove that Bn is decreasing. Why it is decreasing? Actually, it is obvious that it is decreasing because 3n plus 2, when n is increasing, 3n plus 2 is increasing. When denominator is increasing, the overall fraction is decreasing. But you may want to find the derivative of 1 over 3x plus 2 square and show it is negative. So if the derivative is negative, then I can say that 1 over square of 3x plus 2 is decreasing. Okay, now we have all three conditions and find a limit of Bn when n approaches infinity. What is the limit of Bn? It's 1 over square of 3n plus 2, and n approaches infinity. Now, when n approaches infinity, denominator is 3 times infinity, which is infinity. Infinity plus 2 is infinity. And 1 over infinity is 0. Now we have all three conditions. We have alternating sign, and sequence is positive and decreasing, and the limit is 0. So by alternating series test, we know that sigma -1 to power n Bn e converge. Okay, the next problem is sigma -1 to power n sine of 1 over n. The question is this series an alternating series? Although there is -1 to power n, you may tell me sine of 1 over n, or Bn in this case, oscillates between -1 and +1. The sine function oscillates between -1 and +1. So it is not positive all the time, and the derivative is not negative all the time, because the derivative is cosine. And that one oscillates between -1 and 1. So my answer is, because n starts from 1, goes to positive infinity, it is greater than 1, right? So n cannot be 1/2 or between 0 and 1. It is already greater than 1. So you have at least 1, and then you have sine of 1/2, sine of 1/3, sine of 1/4, sine of 1 over 100, you know. And the sine function for these small values always is positive. So here Bn is sine of 1 over n, but the interval is from 1 to positive infinity. For this interval, sine of 1 over n is positive, and we have this condition. Also, you see the negative 1 to power n to alternate the sign and makes the series an alternating series, and it is decreasing. Bn is decreasing. This interval is decreasing. So we have these conditions. The remaining is to find the limit of Bn when n approaches infinity. What is the limit of sine of 1 over n when n approaches infinity? Okay, 1 over infinity is 0. Sine of 0 is 0. And you see that we have all three properties of alternating series test. So I can conclude that by alternating series test, sigma negative 1 power n sine of 1 over n converges. Okay, let me call it sigma an. This is sigma negative 1 to power n bn. Now let's call it sigma an. So the overall negative 1 to power n sine of 1 over n is an. I want to call it an. Now, here I want to add something about the kind of convergence. We have two kinds of convergence: conditionally convergence and absolutely convergence. So what is conditionally convergence and absolutely convergence, and what is the difference? If we have sigma absolute value of an, we evaluate convergence of sigma absolute value of an, and I know it converges. Then sigma an converges absolutely. So I say it converges absolutely. And if you evaluate sigma absolute value of an and it diverges, but when you evaluate sigma an itself, you see that converges. Then you can conclude that sigma an converges conditionally. So we have two kinds of convergence, conditionally and absolutely. If you evaluate sigma absolute value of an and you see it converge, then the sigma an converges absolutely. If the absolute value of our theory diverges but the original theory converges, then the kind of convergence is conditionally. In the previous example, which is an alternating series, you found that sigma an or sigma negative 1 to power n sine of 1 over n converge. So the sigma an itself converges. Now I want to check if it converges absolutely or conditionally. So we need to check sigma absolute value of an instead of sigma an. What is the absolute value of negative 1 to power n sine of 1 over n? So it's absolute value of negative 1 to power n times absolute value of sine. Absolute value of negative 1 to power n is positive 1, and positive 1 times absolute value of sine is absolute value of sine, but sine, I mentioned, for n from 1 to positive infinity always is positive, so you don't need absolute value anymore. So what is the sigma absolute value of an? It's just sigma sine of 1 over n. Now let's evaluate sigma absolute value of an, or sigma sine of 1 over n. What we know about this series, how we can check if it converges or diverges. So it's not possible for us to use direct comparison test because of sign. But let's check and compare this theory with, for example, Cn, which is 1 over n. And by limit comparison test, because we cannot directly compare sine with 1 over n, let's find the limit of sine of 1 over n divided by 1 over n when n approaches infinity. If the answer is a constant less than infinity, then the behavior of sigma 1 over n and sigma sine of 1 over n should be the same. Cn here, or sigma Cn, the series of this sequence, is a p-series. What is p here? P is 1. The exponent of n is 1. In p-series, we know that if p is 1 or less than 1, then the series diverges. Now let's find the limit and see what is the answer. How we can find the limit of sine of 1 over n divided by 1 over n when n approaches infinity. If you plug infinity, you get sine of 1 over infinity, which is 0, sine of 0 over 0. Sine of 0 is 0, and denominator is 0. So it is undefined. But from the Calc 1, you remember there was a formula, limit of sine of u over u when u approaches 0 is 1. U should approach 0. If n approaches 0, when n approaches 0, then what happened to 1 over n? Sorry, when n approaches infinity. 1 over n approaches 0. So here, 1 over n is u, right? And if you rewrite this one, the limit, it's sine of u divided by u approaches 0. So what's the answer? It's 1. And the limit is 1, is less than infinity, then by limit comparison test, the behavior of the sigma 1 over n and sigma sine of 1 over n should be the same. We already know that sigma cn is a p series and diverge because p is equals to 1. So this series diverges. So we can conclude that sigma sine of 1 over n or sigma absolute value of an diverges. So what can we say about the sigma -1 to power n sine of 1 over n or sigma an? We found that sigma an converges, but sigma absolute value diverge. So we can conclude that sigma an converges conditionally. So as a sigma -1 to power n sine of 1 over n converges, but the absolute value of this series diverges, we conclude that the series converge conditionally. This is what I wanted to tell you about the alternating series and alternating series test. In the next video, I go over the root and the ratio test as the last test for checking convergence or divergence for this series. See you in the next video.